fine detail. Well, in 1650, the astronomer Riccioli looked at the brighter of these two stars, Mizar itself, with the telescope, and he saw that it was actually composed of two stars. William Herschel looked at a number of binary stars. He was trying to compare the distances of the two stars that appeared to be together in the sky to see if they were really going around each other. And in 1804, he obtained proof that the two members of a star known as Castor in the constellation of Gemini the Twins, the two stars he could see, were going around each other because he could detect the motion of one of them compared to the other. This not only proved that some binary stars were actual physical pairs, it also was a proof that gravity, Newton's laws of gravity, were universal. They extended all the way to the stars. We now know, of course, that many binary stars are such physical pairs, but we also know that there can be more than binaries in such groups of stars. They can be multiple stars, and in any case, their orbits follow Kepler's third law. That law, of course, relates the size of the orbit to the period, the length of time it takes the star to go around its companion. What we also know, of course, is that these laws that Kepler put together were modified by Newton, explained by him, and that the real relationship between the size of the orbit and the length of time it takes to complete it is the mass of the two objects involved. The period and the size of an orbit, then, are related through the masses of the two objects in orbit about each other. We can use this fact to obtain the mass of something like a planet, like Jupiter, for instance. We watch one of its moons go around the planet Jupiter, and so we can deduce what Jupiter's mass is from this motion. Of course, the satellite's mass compared to Jupiter is practically insignificant. But this doesn't really work for binary stars because the two stars may be of comparable mass. And in order to figure out, then, which star has which mass, how we divide the total up, we have to obtain something else. We've got to determine the position of the center of mass.
Binary stars revolve in elliptical orbits around an imaginary point called the center of mass, or barycenter. A line drawn between the two stars at any point in their orbits will always intersect the center of mass. In order to maintain this configuration, the more massive star of a binary system has a smaller orbit and a slower velocity than its less massive companion. The barycenter of a binary system can be compared to the balance point on a scale. A 1 kilogram mass would have to be 2 times the distance from the balancing point as a 2 kilogram mass to achieve a perfect balance. In other words, whenever the ratio of distance is 2 to 1, the ratio of mass must be 1 to 2. If the ratio of mass is 3 to 1, then the ratio of distance must be 1 to 3. In this way, a mass can be calculated merely by measuring its distance from the balancing point. This principle is an important element in most of the methods used to calculate the mass of a star. For example, 2 stars held together by gravitation have their center of mass somewhere on a straight line drawn between them. The barycenter is indicated by the intersection of these imaginary lines. Because the smaller orange star is 3 times farther from the barycenter, its mass must be 1/3 that of the larger yellow star.
The most fundamental property the star has is its mass, the amount of matter that's contained in it. Now, we have no way of just counting up all the atoms of hydrogen and helium and lithium and calcium and so on, which make up the mass of a star. The only way we can get at the mass of the star is if it exerts a gravitational attraction sufficiently strong on some other object that we can measure its pull on that object. And this is where binary stars come in. They are almost the ideal cases of the classical two-body problem, and so they do move in orbits and follow the classical laws of gravitation, the same kind that the planets follow going around the sun. So what we need to be able to do in analyzing the observations of the different kinds of binary stars is to get the sizes of their orbits, how fast the stars are moving in their orbits, how long it takes them to go around. And it is the securing of these kinds of information that requires different techniques for the different kinds of binary stars, but the end results are essentially the same and lead us then into the determination of masses.
Different types of binary stars found throughout our galaxy are categorized according to the techniques used to observe and analyze them. The first type to be discovered were the visual binaries.
The visual binaries, by their very nature, you have to be able to see them as two stars in the telescope. And if it's too far away, if the system is too far away, the stars will get closer and closer together, and you won't see them separately, so that the visual binaries are going to be preferentially stars close around us in order that you can see them separately. That means that you're not surveying a very large volume of space, and you're picking up the most common kinds of stars, stars like the sun and mainly less luminous than the sun, referred to as lower main sequence stars.
The fact that a binary is visual means that its components are well separated from each other and therefore have long period orbits ranging from a few years to thousands of years. As a result, in order to accumulate enough data for analysis, observations of visual binary systems usually span a number of decades.
For observations of visual binaries, one attaches what's known as a filar micrometer to the eye end of a telescope, and the observer looks through the telescope. He makes his measurements by aligning cross wires in the micrometer, first on one star and then on the other, and measuring the distance between them and their orientation. Now, this might sound like a very simple kind of observation. It is, in principle, very simple. It's been going on for a long, long time. In that sense, it's old-fashioned. But it does require the most consummate skill of the observer to do this carefully, particularly when the stars are very close together, to take advantage of those fleeting instances when the atmosphere is steady.
In order to plot the orbits of a binary system, the astronomer first determines the relative motion of the fainter star, called the companion, around the brighter or primary star, instead of determining both stars' motions around each other. The distance between the two components is called the angular separation. Their orientation with the north celestial pole is called the position angle. This observational data provides the astronomer only with the apparent relative orbit of the binary system, since the actual orbit of the stars is not necessarily viewed face-on to our line of sight. For example, stars which actually orbit in this configuration would, if viewed from some other angle, appear to move in a different path such as this, with the primary star no longer at the focus of the elliptical orbit. The astronomer, then, must adjust for this distortion caused by the angle of view. This is done mathematically. After this is accomplished, the true dimensions of the orbit are evident. This data can then be combined with the period of revolution of the stars and Kepler's third law to yield the total mass of the visual binary star system. To determine the individual masses of the stars, the barycenter must be established. This can be done, for example, by observing the star's proper motion, the actual motion of the stars across the sky. The individual components appear to move in interwoven paths, with each star alternating between one side of the barycenter and the other. Unlike the two stars, the barycenter itself moves along a straight path. Because of this, the astronomer can determine the barycenter's location and, ultimately, the individual masses of the stars in the visual binary system.
The very massive stars, the larger stars, usually aren't found in this kind of a binary system. In fact, lots of times the large stars, the massive stars that is, are so close together they're practically in contact, and they go around each other in a matter of just a few hours. But we can identify these high-mass stars in binary sets. We can also measure them. And we can do this even though we can't actually see them as separate stars. Now, the way we do this is with their spectra.
If the motions of the two stars in their orbits causes detectable Doppler shifts in their spectra, the system is called a spectroscopic binary. For example, as the star advances toward the Earth, its spectral lines are shifted over the continuous spectrum toward the violent end, when compared to a laboratory spectrum at rest. When the star is neither advancing toward nor receding from the Earth, the spectral lines in both the laboratory spectrum and the star spectrum are at rest. But as the star recedes from the Earth, its spectral lines shift toward the red end.
An extremely important application of the Doppler shift is in the study of binary stars. There we find two stars moving around each other, so during part of the cycle, one star will be approaching us and the other going away. Half a cycle later, their roles are reversed. And the spectral lines and the light from the two stars therefore shift back and forth out of phase with each other, showing us how they're revolving around each other. We can analyze that shift on the spectral lines due to the orbital motion of the stars and figure out how fast the stars are moving, how big their orbits are, how long it takes the stars to get around each other, and consequently what the masses of those stars are.
Spectroscopic binaries can be extremely helpful then as another tool to help us obtain basic data about the stars. In that case, we use the Doppler shifts in the spectrum. But unfortunately, there's a complication in our analyses of the spectroscopic binaries. And that complication is we really don't know the angle at which we're looking toward a pair of stars in orbit around each other when we can't actually see the two stars. Well, for instance, they might be orbiting around each other face-on like this, face-on to us. And if that's the case, we don't detect them as spectroscopic binaries at all because we don't see any shift, no Doppler shift, because no radial velocity, no motion in our line of sight. On the other hand, the binary pair may be oriented right in our line of sight, exactly in our line of sight. And if that's the case, then we get the maximum effect of the Doppler shift. But more likely, it's going to be tilted at some angle to us, like this, and the star's going around that way, and we're really unable, just by looking with our spectroscopes, to tell what the angle is. And so we can't really estimate the total sum of the masses of the spectroscopic binary. Instead, we can only put a lower limit on the sum of the masses. Now, there are a few rare cases, and they're very interesting cases, when the stars are in our line of sight, and in fact so perfectly in our line of sight that as they go around each other, one star eclipses the other because it gets in front of it as we see it, and then vice versa. The other star goes in front. And we can pick up these eclipses by observing the change in brightness of the star. In fact, it can be as obvious as the star Algol, sometimes known as the demon star to the ancient peoples in Arabia, who probably noticed that change as well every 3 days or so as the star went through its eclipse cycle. That gave it an odd kind of pattern of brightness that could easily be detected by anyone paying attention. And so we today pay attention to these eclipsing binaries because if they are also spectroscopic binaries, we can obtain not only the exact value of the mass of each star involved, we can also get lots of other interesting information about the stars that make up the pair.
Algol, in the constellation of Perseus, was the first eclipsing binary system to be discovered. In 1669, Montanari observed that the star varied in brightness. A century later, John Goodricke measured the rate and the amount of light variation in Algol. As an explanation, he proposed that the star either had huge dark spots which were brought into view by its rotation, or that it was eclipsed by an unseen companion star on a regular basis. Shortly after Goodricke's discovery, analysis of Algol's spectrum revealed that it was indeed part of a binary star system.
For the eclipsing binaries, one has two quite different kinds of observations requiring the use of different kinds of equipment. For analyzing the motions of the stars, their velocities, their velocities, one makes use of a spectrograph in which the light is fed through the standard type of astronomical spectrograph spread out into different wavelengths, so you can see the spectrum lines of both stars of the binary system and see how the lines change their position. The other kind of observation in which you obtain the light variations as the star goes through eclipse requires what's known as a photometer, a light measuring device, which is usually a photocell of some kind, and records the intensity of the light.
The photometer gathers data which can be plotted on a graph to display the variation in brightness of the eclipsing binary system over a period of time. The graph is called a light curve. Since the components of an eclipsing binary are almost always too close to each other to be resolved into separate stars, the photometer measures the total light output of the system as a whole. The binary system registers brightest on the light curve when neither star is being eclipsed. However, during an eclipse, as one star passes behind the other, some of the light is blocked from reaching the photometer. This causes a drop in the light curve. The largest drop on the curve, or the primary minimum, occurs when the brighter star is eclipsed by the fainter star. The secondary minimum, which represents a slighter drop in brightness, results when the fainter star is eclipsed by its brighter companion. Comparison of the light curve to the horizontal axis of the graph indicates the duration of each eclipse. The Doppler shifts in the star's spectra show their orbital velocity. So by knowing how long the eclipses last and the speed at which the stars are moving, astronomers can deduce the distance the stars traveled during the eclipse, and therefore the diameters of the stars. Subtleties in the light curve provide additional information about the binary system. A flat bottom minimum, for example, indicates that the binary system alternates between total and annular eclipses. A total eclipse occurs when the smaller star passes completely behind the larger one, whereas an annular eclipse occurs half a period later when the smaller star passes in front of its larger companion. A partial eclipse produces sharp bottom minima. Both eclipses are partial if the larger component never completely blocks the smaller component from view. Varying light levels between eclipses indicate that the stars have been distorted into elliptical shapes by their gravitational pull. Beta Lyrae is such a system. This artist's conception depicts how the stars are so close together that they are actually exchanging material. In the process, some of the stellar gas spirals off into space.
Now, we really ought to be able to see the diameters of stars with our telescopes. Our telescopes are large enough to resolve actual diameters of stars. But it's our atmosphere that makes this impossible. Our atmosphere is constantly in motion, and it muddies up the images so that we never actually can pick out the exact diameter of a star. We only see it as a point of light that kind of moves around and is unresolved. But Kitt Peak astronomers are perfecting a technique that does allow us to resolve the diameters of at least some of the largest of the stars. And this technique involves computer processing and electronic light intensifiers, as well as very short fraction of a second exposures that all combined allow us to actually see the disks of a few other stars besides our own suns.
As the light comes through the atmosphere, it gets distorted, and as a result, the best angular resolution that can be achieved with any size telescope is of the order of 1 second of arc. Now, in principle, a large telescope should be able to do nearly as good as 1/100th of a second of arc. And so many of our big telescopes are not achieving what, in principle, they're capable of. Now, the distortion of the light as it comes through the atmosphere results in that 1 second of arc image breaking up into lots of areas of high contrast called speckles. On a photographic plate, they appear as little black lumps. Each one of them is more or less a diffraction-limited image of the object, namely the kind of image a telescope would see if the atmosphere were not in the way, but incomplete and scrambled up among themselves. And the techniques of speckle interferometry are to take that data and unscramble it so that the telescope can, in fact, achieve the angular resolution of which it is, in principle, capable.
When this technique became developed, it appeared possible that it might be just barely on the realm of a possibility to make an image of another star. So we picked the biggest star in the sky other than the sun, and that was Betelgeuse, and tried a technique that was developed with my colleagues Roger Linz and Peter Warden. We tried a technique that we thought would work, and it did. We were able to make a very crude image of another star. There had been some theoretical work which suggested that there would be large-scale temperature patterns on this star, and our observations were aimed at making these temperature patterns visible. We believe that we we're able to say something about the size and magnitude of these temperature patterns. Well, on our process picture, the image shows a lot of structure. Some of that is certainly noise, but we made observations on 4 different nights, and therefore we were able to separate out noise from real effects by comparing the observations on one night with another night. A comparison like that showed that some of the structures persisted from one night to the next. We think that the largest scale features that we saw, the biggest area features, are real.
Measurement of stellar diameters has shown that stars range in size from about 100 times smaller than the Sun to over 750 times larger than our Sun. At the low end of the scale are the white dwarfs, such as the companion of Sirius. These stars are approximately the same size as the Earth. Moving up the scale, we find stars such as Aldebaran, a red giant, which is 36 times larger than our Sun. There are stars even larger than Aldebaran, however. Betelgeuse, for example, averages 750 solar diameters.
Stars vary tremendously in size. When you start thinking of the largest of the stars, huge red giants like Betelgeuse, they're 750 times, say, larger than our own Sun in diameter. Or we could represent for a moment a star like Betelgeuse with our planetarium theater dome, which is 75 feet in diameter. And then if we compare that with, say, one of the smallest of the stars, like a white dwarf, the companion of Sirius, for instance, a star which may be only 100th the size of the Sun, well, that star then, on this scale, would be represented by the point left by a pencil on a sheet of paper. So from a pencil point to the planetarium dome is the range and sizes of the stars. Now, interestingly, the masses of the stars don't vary anywhere near so much as the sizes of the stars. If we think about the low end of the mass scale of the stars, we find stars with a few hundredths the mass of the Sun. Now, they couldn't be much lower than that. If they had less mass than that, they really wouldn't get hot enough inside their cores to allow thermonuclear reactions to go on. So we find stars really no less than that in mass. If we find something else, it's a planet. And even the least massive of the stars are dozens of times more massive than the largest planet we know about now, Jupiter, in our own solar system. Now, when we look at the most massive of the stars, we really don't find anything that's, say, more than 50 times the mass of the Sun. We don't exactly understand why that limit exists, but it seems to be related to the stability, what it takes to keep a star stable. And anything much more massive than that somehow just doesn't hold together. Well, we find then the range of masses of stars varying over about 1,000 times, from the least massive to the most massive. The range in size, however, is much larger than the range of masses. The smallest of the stars, compared to the largest of the stars, are about 75,000 times smaller. So there's a much larger range in size than in mass. Well, we've learned then a number of the basic properties of the stars. But of course, we have to ask ourselves, why are we trying to get this information? What does it mean to us? Well, it's the basic properties of the stars that really tell us what a star is. When we ask what any object is, the only way we can really answer it is, what's its mass? What's its size? What's its temperature? These are the things that give it its identity. And of course, for the stars, what we also then can learn, if we gather this information, is how the stars shine and how they change. Now, almost all of our basic information about the stars comes the hard way. We get the luminosities and the surface temperatures from photometers and spectrographs. And from binary stars now we see that we can obtain the masses and the radii of stars, 2 more basic pieces of information. What happens after we obtain all of this basic information about the stars, their brightnesses and their masses and so on? Then we learn some patterns that we can see in the types of stars that are around us. For 90% of the stars, the hotter stars are the brighter stars. Also now, with binary stars, we learn that the brighter stars are, in general, the more massive stars. And this is the basic mass-luminosity relationship that holds for so-called main sequence stars. Now, these stars are extremely important to us because our Sun is one of them. They're long-lived, stable stars, which we now know are going through thermonuclear reactions, burning hydrogen into helium. But it was the discovery of these facts about the stars, like the mass-luminosity relationship, early in this century, that led to our understanding of the nuclear process. And if that process is mimicked in the laboratory in years ahead, if we can do on Earth what the stars do every day, every moment, and if we can produce controlled nuclear fusion, then we may well solve our energy problems, and this may yet be astronomy's greatest contribution to society.